Good morning, everybody, and welcome to Module 2. This module, we're going to deal primarily with energy, its different forms, and then also how that applies in a biological setting. So how do we use things like enzymes to transfer energy around from molecule to molecule inside the cell? How do we break down molecules to capture the energy that's stored within them? And then also, how do we take that captured energy, convert it into a form that we can all use? But first, we kind of have to talk about and discuss the principles of energy itself, right, and how we think about it. So we'll start with the laws of energy, just because the laws of energy are what everything is actually based on, right? All right, so we'll go ahead and start with the first law of thermodynamics. And the first law of thermodynamics states energy cannot be created or destroyed. So that means the total amount of energy that we started with is the same amount of energy that we finish with. However, it will be different types of energy. So you can start with a lot of free energy. Eventually, that will become entropic energy. We'll talk about that in a minute. Don't want to get ahead of myself. So energy cannot be created or destroyed, but it can be transferred or it can change form. So we can transfer it from object to object, or we can take it from a chemical bond and put it into another chemical bond. We can change form, so we can take like electrical energy, like moving electrons through a wire, and we can change that energy into the energy of light. Like we can power a light bulb, and then the photons coming out of the light are a conversion of the energy that was in the wire now going through the filament in the bulb. So it can change form, it can be transferred. But first, let's define really what is energy. What are we talking about when we say energy? So it exists in two major forms, right? Now this goes contrary kind of what you were expecting. You'd say like, oh, there's tons of different types of energy: kinetic, potential, thermal, nuclear, that sort of. So that's not what I'm talking about. Two different forms of major energy, two different types. The first type is free energy. So that's the energy that can be used to do work. Okay, and we represent it with a variable g. And this is no different than saying like if I want to measure something, like how heavy something is, like this cup is 500 grams, right? So I give it 500 Gs, right? So that's kind of how we do it with energy, is that we give it by the variable G. And we say, okay, like, so what is G? How is G changing in a system? How is the amount of free energy in a system changing? So that's the energy that can harness to do work. And there's tons of different forms of free energy, many of which you are familiar with from high school science classes, like kinetic energy, the energy of moving mass; potential energy, stored energy, right? That sort of stuff; thermal energy, the energy of heat; nuclear energy, the energy of radiation; electromagnetic radiation, the energy of light. So lots of that stuff is all of that is free energy. That's energy that can be harnessed to do work. The other type of energy that we have is entropic energy. And so we call this kind of the radiant thermal energy that cannot be harnessed to do work. And so entropic energy is the energy that leaves a system that's not captured in a transfer. So like if I'm taking a piece of sandpaper, or maybe rubbing my hands together, right? If I'm rubbing my hands together, right? Um, the friction in my hands, the movement of my hands against each other, is creating heat. And when I turn my palms face up, that heat radiates off of my palms. And that energy was actually transferred from the motion into my palms, and now it's radiating away from it. And so that energy is entropic energy. We can't capture it, we can't harness it, we can't do work with it. Okay. And so anytime that free energy is being transferred from something to another place, it loses its ability or its capacity to do work in the form of radiant heat from that reaction or from that exchange. So that's entropic energy. And we'll talk about how free energy is related to entropic energy as we move forward here. We do know, so going back to the first law of thermodynamics, we know that the total amount of energy in the universe will never change. So that means that T, the total amount of energy, is equal to free energy, G, plus S. So the amount of free energy in the universe plus the amount of entropic energy in the universe is equal to the total amount of energy in the universe. Okay. All right. So let's talk about the different types of free energy. Like we said, there was kinetic energy. You're used to that one, right? So that could be moving mass, right? Like a jumping frog moving through air, and a car with a lot of mass moving, like on the freeway. The other type of kinetic energy is the movement of electrons. So from a cloud to the ground, lightning strikes, or even just like powering devices in your house is a form of kinetic energy, the movement of electrons through a wire. We've got nuclear fission. That would be what happens inside stars where atomic masses are joined together, right? We talked about that a little bit last unit. We've got potential chemical energy. So the energy stored in the bonds, the chemical bonds of a piece of wood as it catches on fire, that's chemical potential energy being released. Or better yet, what we're going to talk about more this unit is the food that you eat. So when you consume foods, you have like this, you have sort of a material that you're putting into your body. And within that material, there are bonds that are storing energy. And our body has enzymes or catalysts present that will take the energy from the food molecules and transfer that energy over to something chemical or something biological that we can then use to power reactions inside of our own bodies. So it's kind of this transfer. It's like there's a middleman, if you will, in the process of breaking food down. There's a middleman that takes the chemical energy released from food and transfers it over into biological energy that we can then use for reactions, right? Another important type of energy too is the electromagnetic radiation, and so that's the entire spectrum of light, not visible light. Visible light is just a small fraction of that spectrum. So some examples of EMR would be red, orange, yellow, green, blue, violet. Those colors are an example of electromagnetic radiation. Microwaves, radio waves, right? Those are a little bit slower and longer waves. As we shorten the distance between peaks in the waves of photons, we get down to ultraviolet radiation, we get down to X-rays, we get down to gamma rays, right? So there's this entire spectrum of EMR, and we'll talk a lot more about that when we get to photosynthesis, because plants capture energy of a certain region or a certain spectrum, if you will, when they do photosynthesis. So that's a general idea of all the different types of energy. If you're looking up here at thermal energy is this idea that when we talked about this last module, is that molecules are always in motion, right? There's a certain vibration to molecules. If those molecules are cooling, if they're in an environment that's cooler than they are, that environment will absorb some of their thermal energy, right? So some of their energy will be lost in the form of heat, like entropy, and the environment absorbs that, but you're not able to do work with it. So thermal energy is sort of like this idea of it's how much energy is within your motion of vibrating molecules at a certain temperature. I know it's a little bit tricky, right? So we talked about first law, right? We got the total amount of energy in the universe is G plus S, is the amount of free energy plus the amount of entropic energy. The second law of thermodynamics is very important because this is like everything has to function off of this law. You cannot violate this law, okay? Free energy spontaneously becomes entropic energy in a closed system over time. And you're like, okay, well, it's a closed system. Well, an example of a closed system would be like the universe. So the universe is a closed system. A closed system is something in which energy cannot enter the system, energy cannot leave the system. So technically, right, the universe could be a closed system. If you're not consuming food, your body is a closed system. If you're not putting things into your body is essentially a closed system. Now, the caveat to that is that obviously you're a warm body of mass. Usually the air around you is a little cooler, so you're losing a little bit of thermal radiation, right? You're losing a little bit of entropy from your body over time. But the idea, though, is that if you do not keep putting food into the system will eventually break down and become entropic over time, spontaneously, all on its own. If I leave firewood sitting in the forest for millions of years, it will eventually break down to the point where it will no longer catch fire, meaning that there won't be enough potential energy in the bonds of the wood to combust and create a fire. So this idea that over time, right, things that have a lot of free energy will eventually lose that free energy, or that free energy will spontaneously start to become entropic over time, is fundamental principle of second law of thermodynamics. Okay, so free energy will slowly and irreversibly become entropic over time. Yeah, so eventually, right, this is one of the irrational fears of modern man, is that eventually all of the free energy, if we plot this line, this trajectory of free energy turning into entropic energy, if we plot it over time, we can see that wait a second, the whole universe is going to burn out eventually, right? Like all the free energy in the cosmos will eventually become entropic, and no reactions will be able to take place. And this is true, but you also have to imagine that we are just alive during a small sliver of time, and so our sense experience is allowing us to construct models that can predict this sort of stuff in a short range of time. But when we're talking about the lifespan of a universe, we have no idea, right? So, but in the short term, right, and as far as we're concerned, and how functional this idea is, it's 100% functional because it governs everything that happens in our time frame that we're used to. Okay. So we still need to define what an open system is, right? So we said what a closed system is, something that energy cannot come in or out of. But an open system is a system that allows the input of output of energy. And so an open system would be something like your body, where you're putting food in, you're pooping food out in a changed form, right? The food you're putting in your body is technically at a higher energy level. The stuff coming out of your body has a lower energy level. So a good example of an open system would be the planet Earth. Okay, so we on planet Earth, like if we didn't have a sun, we would eventually turn very cold and become about the same temperature as the rest of the space around us, almost absolute zero. But because we're an open system, because we have because we have electromagnetic radiation coming in from the sun in the form of the visible light spectrum and all other light spectrums, right? Because we have that energy coming in, we're able to use that energy, capture that energy, change its form, turn it into different things. So plants take that energy in, put it into molecules like sugar that can store that solar energy in the bonds of sugar. And then us animals will either eat animals that eat that sugar, or we'll eat that sugar ourselves. Okay. Um, Another example, right? The refrigerator is requiring electricity from outside in order to do work to keep the food cold. So in order to run the compressor and stuff, it requires energy. Okay, closed system, we already described that. Hermetically sealed room, right? Nothing can get it in or out, or a human body, right? As long as you're not like eliminating food or eliminating waste and not eating anything. Okay. Obviously the universe itself. Yeah. Okay. So let's talk about like how free energy changes in a closed system, right? We'll just pretend that we're talking about a closed system for now. So if it goes from a high over time spontaneously, if it goes from a higher energy state to a lower energy state, what would be the change in free energy of that system? So we started with more, we ended up with less. Would we say that was a negative change or a positive change? It's a negative change, right? So we'll take the final energy. Let's just say it's 5, right? And the original energy, let's say it was 10. So final 5 minus 10 would be negative 5. So we lost 5 G's of free energy from that system, right? From that reaction. So we talk about the change in free energy as that little triangle shape. And that triangle shape is the capital Greek letter D, delta. And all it signifies is it says, okay, what is the change of this variable? And in this case, we're talking about what is the change of this variable of free energy. And that change is negative when you lose free energy from a system, right? And so here, let me give you some examples of this, like free energy spontaneously becoming more entropic energy, right? So on the top bar up here, right? Move my camera out of the way. Up on here on the top bar, we've got molecules that are tightly packed together. We've got, this looks like a sugar molecule. So you got some black carbons in there, the red oxygens and the gray hydrogens. So a sugar molecule. Then we've got this guy standing on a diving board, nice and tall above the water. And so all of these systems are representing more free energy, right? Molecules packed closer together are going to have, there's going to be more strain on them pushing against each other. There's going to be more free energy in that system. The chemical bonds of glucose are less stable, but they have, but they have higher free energy. Where are we going? They're stable. They're less stable, and they have more free energy. So they can break down easier, but they have more free energy. The guy on the diving board, right? So he's representing a distance away from the center of the Earth, and there's a gap there, and so that he can go from a state of potential energy up here on the diving board and transfer that into kinetic energy just by falling off the diving board. He doesn't have to jump, he just falls and his potential energy becomes kinetic. And so this idea of gravitational motion or diffusion or a chemical reaction, these are all spontaneous events. These are all spontaneous actions, meaning that these will happen in a closed system on their own spontaneously, right? If we don't do anything to this guy on the diving board, we don't feed him, we don't give him anything, he just sits up there for weeks and weeks until he becomes emaciated and then dies. He falls off. He falls off the diving board eventually. Eventually, he will fall. Right? It doesn't require the input of any sort of energy. Diffusion of molecules. So when you have molecules that are in a tightly packed space, they diffuse spontaneously. Just think like a fart, right? Somebody farts, right? Those molecules are highly concentrated. It diffuses into the room. That doesn't require any energy. It does that naturally on its own, and then everybody smells it. And then you have your glucose molecule, and that will spontaneously break down on its own into carbon dioxide, which is this carbon with two oxygens, and water, which is the oxygen bound to two hydrogens. And so these molecules down here are much more stable, meaning they're harder to react with than glucose. Glucose is much easier to react with. It has more free energy. It can do more stuff. It can do more work. Whereas these molecules down here, water and carbon dioxide, pretty inert molecules. So this is the idea of the second law of thermodynamics, is that things go from a high free energy state to a low free energy state, or a high entropy state, or equilibrium, or diffuse, or whatever, right? Spontaneously. So now let's talk about that change in free energy in a system due to like chemistry, like how things react together. So we'll look at two different types of chemical reactions, and these ones we're going to use. We've already used them in last module. I introduced them there, but I'm gonna bring them in and reinforce them in this module, because we can use these two types of reactions to describe just about everything that's taking place inside of a cell. Okay, so the first type of reaction is an exergonic reaction. Okay, so an exergonic reaction is this idea where the total free energy of a system is going to start high and finish low. So you can think about this as sort of like glucose breaking down into carbon dioxide and water, but also like gasoline combusting in the engine of a car. Gasoline has a lot of free energy. When it goes through combustion, that free energy is released, moving a piston, right? Changing the potential chemical energy inside of the gasoline is changed into kinetic energy as it combusts and moves the piston up and down in a car. That turns the crankshaft, turns the axle, turns the wheel. Gasoline combusting is an example of an exergonic reaction. So think X means like exit, right? So that would be the exiting of free energy from a system. Okay. An endergonic, right, reaction, like entering a system, right? That's where the free energy of a system increases from start to finish. So you've got, so endergonic reactions are where free energy is entering a system. So if you think about the final state of a system minus the starting state of a system, right? That was how we measured the change in free energy. So that means if free energy enters a system, right? Maybe that system had 5 free energy. And let's say 5 free energy enters the system. That means that system now has 10 free energy. So the change in free energy is the final minus the initial. So 10 minus 5 is 5. So there was a gain in free energy, or the change in free energy of that system would be positive. And that's an endergonic reaction. So an example of this would be something like let's say you go work out, right? And you tear up your muscles a little bit. Now your body has to build or repair that muscle tissue after a workout. And so after you work out, what are you, hungry? Yes. So you're bringing in energy from outside your body in order to fuel the repairing activity of your muscle fibers, right? Another example of that would be like, here's one that's external to biology. You've got lumber and you've got nails and you got a hammer, right? It requires you, that the house isn't going to build itself. It requires the input of energy from an outside source in order to order and construct it into a large building or object, right? And so that would be an endergonic reaction, where energy is entering a system and making it have more free energy. Okay, so what I want to point out here on this next slide, so we've got 2 types of chemical reactions, and they each have their unique set of characteristics. Endergonic reactions require input from an outside source. So a lot of times that's like ATP, like adenosine triphosphate. That's the molecule of energy for the body. So endergonic reactions require free energy from outside. They have to happen in an open system by definition, meaning like an open system is one where energy can come in and leave. And so it requires the input of free energy. So therefore it must be an open system. And delta G is always positive. So whenever free energy enters the system, it's always going to be positive. And then we assign some other terminology to this. We say Okay, well, this is an anabolic or a building activity, right? So endergonic, I just worked out. I need to build my muscle fibers. That's anabolic, right? People take anabolic steroids to build up their muscles, right? Anabolic or building. Endergonic requires free energy from outside a system. Some examples of this we talked about last module was that whenever we take monomers and we have to glue them together through a dehydration reaction, whenever we take monomers, glue them together to make polymers, we're going from simple, right, stable monomers into a complex form, which is the polymer, right? So we're going from a more disorderly state where things are kind of like wherever they want to be into an ordered state where we actually have them aligned and connected together. Okay, so that would be endergonic, going from simple to complex, putting energy into a system, right? Building, anabolic, right? Exergonic reactions, though, is this idea of like combustion or free energy leaving a system from a reaction. Okay, this will happen no matter what in a closed system over time. So, firewood breaking down in the forest over millions of years, that happens spontaneously over time, right? That it loses its free energy. We always know because by definition, when you lose free energy from a system, the delta G is going to be negative, right? We consider this to be catabolic. So this is the activity of metabolism. This is the activity of you ate a bunch of food that has a bunch of free energy in it. Now you need to break down the food particles. And so if you're looking at the food particles as their own system, they're going from a high energy state being broken down and having their free energy removed from them. Now, granted, that free energy gets transferred into biological molecules, but even that process of breaking down and transferring, you're still losing free energy in the form of heat. That's why you have body heat. That's why your metabolism generates heat. And this is called a catabolic or a destructive reaction, something that's breaking things down, turning them from a high free energy state or a high state of order into a state of equilibrium, chaos, randomness, disorder. Okay. An example of this would be you have a polymer that's like a bunch of beads on a string, right? And you start chopping them up, breaking off the monomers, and then the monomers go wherever they're going to go, right? They diffuse into the environment. But the polymer was a state of high order, high free energy. So it goes from order to disorder, from free energy to entropy, right? Is exergonic. So let me just get, here's a visual representation of that, right? So on the y-axis, this is free energy, right? So the higher up the y-axis, the more free energy we have. And then the x-axis is basically time, the arrow of time, right? How the reaction is progressing forward. So in an exergonic reaction, right, we start where our reactants, those are what are reacting, right? So that could be like enzymes and foods you just ate. Right? Those are reacting together through time. Energy is being released from that. Let me see if I can get my pointer going here. All right. Energy being released from that system, right, into the environment. Being released from that system into the environment. And when it all said and done, right, your products, what you're left over with at the end is going to have less free energy than what you started with. And so the amount of free energy decreases, which means delta G is less than zero, negative, right? It's a release of free energy from that system. Okay. Endergonic, contrarily, is where energy comes in from outside. And so you have reactants, right? So this could be like carbon dioxide and water if you're a plant. Energy comes in from the sun. You take that energy and put it into the bonds of carbon dioxide and water, and then you're left with sugar. And so your products have more free energy in them than your reactants did, than what you started with. And so free energy increases as the reaction goes forward, but it requires energy to come from an outside source. Okay. Now we ask this question, in the body, what molecule in the cell would be supplying this energy? So um, let's say that you are a plant and you're trying to convert sunlight and carbon dioxide and water into sugar. So what molecule is supplying the energy in that system? It's going to be the sun. That's right. Now, inside of a body like ours, right, we're going to use a different molecule to fuel our endergonic reaction, right? So what molecule is fueling endergonic reactions? That molecule is going to be ATP. Now, go back to our macromolecules lecture, right? Our macromolecules lecture has a molecule just like this in it, right? It's got a 5-carbon sugar, a nitrogenous base, and 3 phosphate groups attached. What type of biomolecule is this? All right, this is ATP. This is a nucleic acid. So this is one of the biomolecules, this nucleic acid. And we consider this to be a polymer, not because this monomer is bonded to another monomer, but we kind of consider these phosphates to be in a polymer form because there's 3 of them attached. Now, something to consider here, this phosphate group is or this phosphorus atom is stabilizing the oxygens around it, right? Each one of these operates as an individual unit. Each oxygen is pulling electrons towards it. And so what ends up happening is you get a lot of bond strain between these 3 phosphates, meaning like it's like taking 3 negative or 3 south poles on a magnet and trying to smash them together and locking them into place. Well, all they want to do is burst apart, right? And so this molecule actually has a lot of free energy because of these 3 phosphate groups. The strain of all those electrons from the oxygens is so great that they just want to pop apart, right? They just want to combust in a way, if you will. So that's ATP. And so what ends up happening is ATP is hydrolyzed, meaning that water comes in and just like we do for our polymer to monomer reaction, where we take water and split it, that's exactly what happens here. We take a water molecule, we split it, we attach a hydrogen on here and OH here, right? And so that's the water molecule being split. And one of the phosphates pops off. Now that reaction going from 3 phosphates down to 2 and 1 leaving also releases a ton of free energy. And so this energy, this free energy release, can be captured by an enzyme or something in the system. This can be captured and transferred into any sort of activity. So this could be transferred into an endergonic activity where you're anabolically building muscle tissue, right? By hydrolyzing ATP. Another thing, this could also power muscle contraction itself, is that this phosphate group popping off, right, causes the muscle fibers to contract, right? And then when that phosphate group pops off the muscle fibers, it relaxes again. So ATP comes in, drops its phosphate group, contracts it, phosphate group pops off. And so you have this activity of phosphate groups popping on and off of molecules, creating action or activity in those molecules. Okay. All right. So, quick question. Since energy is released from the hydrolysis of ATP, right? Since energy is released from that, what would be the sign of delta G of this reaction? It would be negative, right? Because we lost free energy. We had more free energy here, right? Free energy of 10. After we release this free energy, right? We have free energy of 5. So 5 minus 10 is negative. So we lost free energy. Reaction. Free energy was released. It's an exotonic reaction. Okay. ATP is not the only molecule that can store energy for the cell, but it is the most useful, and we'll talk about why on this next page. So I call ATP a cellular battery, and when you think about batteries, you can think about them, especially cellular batteries, you can think about them being like the rechargeable kind, where you can put a bunch of energy into the battery, and then you can take that battery and put it somewhere else and power something for a while until the battery's drained. Then you take the empty battery, bring it back, plug it in, fill it back up with energy, take it, power something else, right? And so that's why I call these cellular batteries, because they have 2 forms. They have the form where they're fully charged, and then they have the form where they're fully uncharged, like where they've released their free energy. Okay. And there's 4 that we're going to talk about in this module. Okay. Like I said, it can exist in 2 states. So charged or uncharged, reduced or oxidized. And those are interchangeable, okay? When something's charged up, I typically say it's reduced because it has extra electrons. Think of battery, right? A battery is charged up when you plug it in and dump a bunch of electrons into it. So that's charged up. We call that reduced because it gained a bunch of electrons. And so its charge, overall charge is dropped, right? Because electrons are negatively charged. When it goes and gets plugged into a device and those electrons are used up, we say it now becomes oxidized. So it lost its electrons or it's uncharged. And so that's why I put these in the same column, as they're basically saying the same thing. Now, the cellular batteries that we use in the cell, the first one is nicotinamide adenine dinucleotide. Okay, the H is just the hydrogen bringing an electron onto it. So the H's in front of it just kind of give you a clue that, oh, there's an extra electron on it that was brought there from the hydrogen. And so that's what gives it its power. When that hydrogen leaves, right, now NAD, like nicotinamide adenine dinucleotide, is missing that electron, and so it has an overall positive charge, and that's why it's NAD plus here, okay? And that's just one molecule. So this is a dinucleotide. So this is actually a polymer nucleotide. And I know that's just a lot to take in. Maybe you can, if you're really interested in what it looks like, you can look it up. So that's nicotinamide adenine dinucleotide. What's interesting about NAD, though, is that it's energetic currency, if you will, right? How much G it's worth, right? If we were to convert that into dollars, is it's worth $5 bill. So it's actually the most powerful cellular battery that we have. And then there's FAD, so that's flavonoid adenine dinucleotide, and it's got 2 hydrogens attached, but it has a little bit less free energy, and that's based on the structure of the flavonoid. It's not based on the hydrogens attached. So they're bringing electrons over, but they're not as energetic. And so the energy currency of flavonoid adenine dinucleotide is basically like a $2 bill. And then of course we have ATP, right? ATP is the fundamental currency that all biological molecules and reactions operate on, because ATP is essentially worth $1. And I'm gonna tell you why it's important that we only use ATP in our cellular reactions. Now, when we get to photosynthesis, you're gonna see another cellular battery called NADPH, right? Or nicotinamide adenine dinucleotide phosphate. Okay. And it works just like NADH. It's got a P in it, so use that to remember that it's in plants only. And that one actually is less than NADH, like in our body. So its energetic currency is only about the same as ATP. Okay. All right, so here's something to think about. ATP is widely used, so it's used almost all endergonic reactions in the cell uses ATP. Here's the part that's important. Most reactions only cost $1 or less. Remember ATP, let's go back. ATP is only worth $1, right? And so most reactions are only worth $1. They only require $1 to kick off. But here's the thing, right? Reactions don't give you change back, right? So let's say the reaction costs 70 cents. You spend the $1 of ATP, you don't get the 30 cents back. Guess where that 30 cents goes? Because we're using energy terms. That 30 cents leaves the reaction in the form of entropy, radiant heat. And so think about it. When your body is taking ATP and it's burning it up and it's using it to build tissues or operate muscles or break things down, all of the change that's not being used, that's being released in thermal energy, is your body heat. That's your thermal energy that's radiating away from your body. That's coming from the reactions of ATP hydrolysis. Okay, so what that means NADH, right? Our $5 bill and our $2 bill, they exchange, like it's some sort of currency exchange in the cell for ATP. So it's like I give you a $5 bill, you give me 5 ones, and then I can go spend those ones. And sure, maybe I'm losing 20 cents here and 10 cents there, but at least like if the reaction costs 70 cents, I'm not spending a $5 bill on it and losing $4.30. So that's why we can use NADH and FADH2 to capture large amounts of energy as we're breaking molecules down and transferring their energy into these batteries. We can use them to capture a lot of energy, but we need to convert that energy that they've captured into $1 bills or into ATP. This exchange is going to take place in the mitochondria. All right, so let's just show how ATP works on a number of different processes in the body. So what we have here, this should look familiar. This is a transmembrane protein. So all it's going to do is it's going to take a molecule from inside the cell and it's going to transport it outside the cell. But here's the problem, right? If the concentration outside the cell is higher, right? If the molecules are packed in closer together, they want to naturally diffuse into the cell. But maybe the cell doesn't want that. Maybe the cell wants to just get rid of these molecules from inside of it. Well, that means that it's moving the molecule against its concentration gradient, meaning that it's going upstream, if you will. Well, that's going to require the input of energy from an outside source. That's sort of like you can take a bucket of water and dump it on the top of a hill, and it's going to run down the hill spontaneously. You cannot take a bucket of water from the bottom of the hill and just wait for it to end up at the top of the hill. You have to carry it there. And so this ATP is going to provide the carrying power to transport one of these molecules from inside the cell to outside the cell. And so the way that this works usually is that this phosphate group pops off and onto the transmembrane protein. And because remember that phosphate group has all those oxygens around it, which love electrons and they're super negatively charged, they change the shape of the protein. So they push against the protein and cause it to change its shape. Well, that change of shape causes the protein to open from inside the cell to outside the cell. So it's acting just like a pump. Now, once it's opened up and the molecules popped off, well, then the phosphate group can leave. And once the phosphate group and that negative energy leaves, it changes the protein shape back again to face the inside of the cell. And so that process right there was endergonic. It cost us energy. Energy had to come from an outside source, right? Change in delta G is positive in this system, okay, from that work. Another thing that it can do, so this is like for muscles, right? If you need to move your muscles, ATP will come on, attach a phosphate. It then powers the motor protein to take a step forward. The phosphate pops off and the next one steps forward. ATP pops on. So you can think about it as just like it's providing the power to move this motor protein down the fiber, right, to transport stuff. All right, so here's an example. Now this whole slide looks really complicated, so we're gonna break it down nice and slow here, okay? What we have is we have two monomers, right? We have glutamic acid, which is an amino acid, and then we have ammonia, okay? And what we want to make is we want to make glutamine, and glutamine is an amino acid, and so we want to take glutamic acid, attach an ammonia to it to make glutamine. So we're going from almost like two monomers to a polymer, which means that that's going to require energy to put those two things together. And so if you look, the amount of energy that that's going to cost is 3.4 kilocalories per mole. And we didn't really talk about moles or kilocalories or anything like that. But what you are familiar with is you're familiar with just calories, right? So like if you eat a bowl of cereal, look on the back of the label, and this is why I asked you guys to do nutrition labels, is it tells you how many calories are in that bowl of cereal, okay? For this one reaction, right, it's going to cost 3.4 calories, like you would see on a cereal box, for 1 mole of this substance. And a mole is just a unit of measure, right? So if I want to make you can exchange mole for dozen, right? So if I want to make a dozen of these molecules, it's going to cost me 3.4 calories to make that dozen of these glutamine molecules, right? Okay. So that's the big picture, right? That's if we zoom way out and just say, okay, we want to go from these two monomers into this polymer. It's going to cost us some energy, right? It's going to require the input of energy from an outside source. So here we're going to break it down into steps. First, ATP is going to come along and it's going to add some free energy to glutamic acid. It's going to attach a phosphate group to it, okay? So that was an expenditure of some energy here, right? Now ammonia is going to come in and it's going to use the energy of that phosphate to attach itself to the glutamine, and that makes, or to the glutamic acid, that makes glutamine. And so the ATP is what's fueling this reaction forward. ATP combusts, that transfer of energy goes on to the glutamic acid. That glutamic acid now has, it's called a phosphorylated intermediate because it's the intermediate step between the beginning and end, and it has a phosphate group attached. Now that phosphate group can power the reaction to attach that ammonia group to it. Now it becomes glutamine. Here's the thing, right? So if we're going to look at this whole equation and how all this stuff works out, remember, right? This is just think calories on a cereal box per dozen molecules, right? So in order to make 1 dozen of these glutamine molecules, it's going to cost us 3.4 calories per dozen of them, okay? All right, that's great. Well, what's providing us with that free energy? It's ATP. This is what I'm talking about. This is that currency exchange. All right, so this goes back to our currency, not our currency exchange, our sort of like a store analogy, right? So we need to go buy something from a store that costs $3.4, right? And I know my number analogy is going to be a little bit off here, right? But it's going to cost us $3.4 from the store to buy this reaction, to buy this glutamine molecule, okay, for a dozen of them, right? A dozen glutamines are going to cost us $3.4. Well, I'm going to bring my currency, my energy currency of ATP in there, and I'm going to spend it. Now, in this situation, right, the ATP is worth $7. So I spend the $7, right? That's the energy of ATP. I spend that, I release it. I don't get change back, but at least I was able to buy this molecule by the dozen. Granted, my byproducts are a wasted form of ATP, right? It's adenosine diphosphate, an inorganic phosphate. And so this idea is that I wanted something from the store, right? I wanted a molecule. it required an endergonic reaction to get it. I used my $1 bill, so to speak, to come in and pay for that reaction. And that reaction then didn't give me change back, but it was able to move forward. And so what you can look at is you can say, okay, well, how much energy did I actually like lose from that reaction? How much change was lost? Minus 3.9, right? Because it only cost me $3.4. I had 7 that I spent, right? So I lost 3.9. So as you can see, most reactions in the cell cost less than 1 ATP. And so that's why we need so many. That's why we need to convert the other cellular batteries into ATP. Okay, let's move on to the next slide. So we can ask the question, right? So there's an invisible molecule here that's facilitating this reaction that is not pictured in this reaction, okay? There's an invisible molecule. And I'll tell you what it is in just a second. But first, let's talk about catalysts. The invisible molecule is a catalyst, right? So a catalyst is a facilitator of a reaction. The definition of a catalyst is that a catalyst is an agent that speeds up a reaction but doesn't get consumed by the reaction. An example of this, right? Can we think of some real life catalysts? There's one on your car. It's actually called a catalytic converter. Some of you might have an old car where you needed to replace this thing. Some of you may be from California, and California has some really, really strict regulations on catalytic converters. Catalytic converters sit at the end of your tailpipe. They come after your muffler, and their whole job is to take unburnt fuel and combust it in the tailpipe, right? And the reason why is because unburnt fuel coming out your tailpipe pollutes the atmosphere like nobody's business. So a catalytic converter helps to reduce emissions or reduce pollution. A catalytic converter is made out of a bunch of heavy metals that as these molecules, these unburnt molecules fly by it, the heavy metals react with it and cause it to combust in the tailpipe. Those heavy metals don't change over time. They stay the same. Now, granted, over like the 20 years of your car running, right, eventually like entropy enters the system. These things will break down spontaneously, right? But in that reaction, it's really not being changed, right? Because it continues to do it over and over again. That's a catalytic converter. Okay. Some other examples of catalysts, right? You'll see you have some firewood sitting out, right? It's not just going to combust by itself. It needs a catalyst. And so you could take a match, right, would be a catalyst for starting that fire. The match itself is consumed by the fire at the end of the match, but that catalyst is not consumed by the firewood itself. Like I light the fire, I transfer the fire to the wood, that starts the wood's reaction, and it's no longer burning up the match once I've transferred that energy there. So that's not a perfect example. Catalyst, an example of a catalyst inside the body would be an enzyme. And so a catalyst is a general term, right? As something that speeds up a reaction without being consumed by it. So you can have catalysts like in your car that you can have catalysts that are not enzymes. And you can have proteins that are not enzymes. But a protein is a catalytic, or an enzyme is a catalytic protein. Sorry, my kid's screaming. I got to pause this for a second. Okay. All right, so an enzyme is a catalytic protein. Okay, it's a protein that facilitates a reaction. We know that proteins do a lot in the cell. We know you got like transmembrane proteins, you've got transport proteins, all kinds of proteins. Enzymes are a specific type of protein that help to facilitate reactions. And so what enzymes can do is they can lower this energy threshold that's necessary for a spontaneous reaction to take place. So for instance, right, remember that firewood will turn into carbon dioxide and water if it just sits in the forest long enough, right, for millions of years. But we can take and we can catch that wood on fire, and it can go through its combustion, its reaction way faster. But we have to invite energy into that system and raise the free energy of that system just a little bit in order for it to spontaneously react quickly. So we call that an energy threshold. So you could say like firewood has an energy threshold that if I overcome that energy threshold by lighting a match and sticking it under the firewood, now it's on fire and now it burns up quickly, right? And so it's the same thing with molecules in the cell. Enzymes have names, and we attach the names ASE to the end. And so we say like, okay, well, that's sucrase, or that's hexokinase, or that's another kinase. That's a, and so they all have the ASE designation at the end of their name. So an example would be sucrase. So what ends up happening is that enzymes are what facilitate reactions in the cell. Enzymes are what facilitate endergonic and exergonic reactions in the cell. They basically help the process move along quicker. When we're doing reactions in the cell, oftentimes we have what we call a redox reaction, right? So we have a reduction and an oxidation happening at the same time, okay? So a redox reaction is when you take an electron from one molecule and you transfer it to another molecule. And so anytime that electrons are exchanged from one molecule to another, right? So let's you take a battery that's dead and you go to charge it up. Electrons are being transferred from the wire into the battery. That's a redox reaction. The wire is being oxidized and the battery is being reduced. It's gaining electrons. Okay. And this happens, redox reactions happen all the time in metabolism with enzymes. And so that's why we're talking about redox reactions. Yeah. So reduction is when you gain an electron, right? When you gain an electron. All right. So reduction is where the molecule that's gaining the electron is going to have a lower charge, meaning because electrons are negatively charged. So when it gains an electron, it reduces its charge. That's why we call it a reduction. Oxidation is anytime that a molecule loses its electron, it becomes oxidized. So oxidation is anytime that a molecule loses the electrons. So the wire in the wall that's charging up the battery loses its electrons, it technically is becoming oxidized. So if you think about it, anytime that a redox reaction takes place, anytime that electrons are transferred, one molecule has to be getting oxidized. Something is getting so anytime something's being reduced, anytime something's gaining electrons, that means those electrons came from somewhere, and that thing has to be oxidized. Okay. So let's talk about it with free energy. Okay. So whenever we say a molecule is reduced, right? So whenever it gains electrons, we also say it increases in free energy. And so this is the idea of charging up a battery, right? So you plug a battery in, it gains electrons, it becomes reduced, it increases its free energy and its capacity to do work. Okay. So an example of this would be like if we take our nicotinamine adenine dinucleotide and we charge it up, right? We attach that hydrogen with a very energetic electron to it, then that molecule is becoming reduced, right? That would also mean that another molecule is becoming oxidized, right? So if we're reducing NAD+, we are also oxidizing something else, okay? So whenever we oxidize something else, its free energy is decreasing because it's losing an electron, right? So if you think about it, if we're breaking food down and we're taking the electrons away from the food and putting it into our cellular battery, we oxidize the food and reduce our cellular batteries and charge them up. Okay. So here's an example of that. If we take FADH2, flavonoid adenine dinucleotide, right, and we remove its electrons from it, right, it becomes an uncharged battery, right? We oxidize it. It loses its electrons and becomes FAD. Here's an example of an enzyme performing its job, doing its duty. We're going to look at sucrase. Now, sucrase is something that they'll use in factories to break sucrose down. So sucrose, if you this is just a slight tangent, right? So we're brought up now, it's sort of a cultural thing where we have somehow adopted the idea that high fructose corn syrup is the devil and it's what's killing everybody, right? But all high fructose corn syrup is it's somebody that took cane sugar, sucrose, which is pure cane sugar. They took an enzyme sucrase, they exposed sucrose to the enzyme sucrase, and they just cut the bond. They cleaved the bond between the glucose and fructose. They also hydrolyzed water, right? So that's what you do when you go from polymer to monomer. So they did a hydrolysis. Or I'm sorry, yeah, hydrolysis, right? They went from polymer to monomer, did a hydrolysis. And it was facilitated by sucrase. And now you have fructose and glucose in a syrup, right? So that would be how you make high fructose corn syrup. Now, this activity of breaking down this bond in sucrose releases a bunch of free energy. And so going from polymer to monomer using this enzyme, it's facilitating that reaction and releasing a bunch of free energy from the molecule. So the question is this endergonic or exergonic, right? And here's your clue right here. Is it endergonic or exergonic? It's exergonic. That's right. Does it happen spontaneously? Would that happen on its own? Would sucrose spontaneously turn into glucose and fructose? The answer is yes, it will. So the question is, okay, wait a second. If it spontaneously will, if sucrose, like table sugar, will spontaneously turn into glucose and fructose on your counter, why doesn't it happen in your pantry? right? And the reason why is that there's a transition state, right? So this goes back into our firewood conversation, right? So we have some firewood, we have some sucrose, right? Some firewood that has a lot of free energy in its bonds. In order to break it down, in order to combust that firewood and release its energy over time, we have to put some free energy into that system. So in order to break sucrose down into glucose and fructose, in order to break that down, we have to put some free energy into that system, and then boom, it'll break it down. All right. And what we call this hump, right, this energy hump, we call it the energy of activation, or sometimes we'll draw it as E with a sub A next to it. And so often, this energy comes in the form of like thermal energy from the surroundings, meaning like it'll absorb energy from its surroundings, like heat, and that, like, for example, firewood, right? It absorbs the heat from the match, right? And then it's able to combust itself into carbon dioxide and water. Okay, so here's what an enzyme can do, though, and this is really cool. So take your normal course of action, right, where you have a large energy of activation, right? So you're going from sucrose down into glucose and fructose, and normally that would require a lot of free energy to come in to make that happen. So what an enzyme does is it will lower the energy of activation of a reaction. So it'll bring down the amount of energy required to come into the system in order to break it down. And so the enzyme does a really good job doing that. The total change in free energy, though, is unaffected by the enzyme, right? The enzyme is just saying, here, I'll give you a push to get over the hill, and I don't have to give you as big of a push because I'm an enzyme. So the question is, how could we speed up reactions, right? Because obviously we want to break things down in our bodies. We eat food, we want to break them down, and we want to capture that energy and put it into our cellular batteries and use those to power energonic reactions in the cell. So how do we speed up all of these reactions? Well, there's two ways, right? The first way is you can add heat to the system. Anytime you add heat to the system and heat the reactants up, boom, you're gonna create a reaction faster, right? So because heat's coming in from the system, you're adding free energy to it, and you're bringing the reactants above their energy of activation, and then boom, the reaction's going to happen faster. So an example of this, right, would be gasoline and combustion. So gasoline is sitting in the tank of your car, it's got a lot of free energy, but if it just sits there, it's not going to combust, right? It's not going to just, well, it might, but if it's like summertime in Phoenix. But for most people, if they just leave gas out, it doesn't explode, right? But if you put it into your gas, or if you put it into your engine, and then you add a little bit of spark, you add a little bit of free energy, it brings the gasoline above its energy of activation and it combusts. So we heat it up, and that would work. You can also use a catalyst. So a catalyst in general, like an enzyme, helps to lower that energy of activation, that threshold. So we call that an enzyme in biology. So two things. If you can bring the reactants above their energy of activation, and notice sometimes they exchange it like a lowercase a or an uppercase a, it means the same thing, energy of activation. If you bring the reactants above that threshold, then the reaction will proceed quickly to completion. And then when it's complete, when the reactions are all done, the molecules are stable, right? They're not reacting anymore. What's left over is not reacting anymore. The wood, right, the complex wood that turned into carbon dioxide and water are stable, and it's at equilibrium, right? So that's when the free energy in that system was released and converted into entropic energy. All right, so we can ask, okay, so what sort of reactions in our systems are going to require enzymes, okay? And the first one that we come to is glycolysis. And glycolysis is just a series of reactions inside the cell, inside the cytoplasm, that take glucose and they break it down systematically, right, in a series, right, that's facilitated by enzymes. They break down glucose, release its free energies from its bonds, and they charge up NAD and ATP from the process. So nicotinamide adenine dinucleotide and adenosine triphosphate are charged up from the breakdown of glucose in a process called glycolysis. Okay. Then you have the Krebs cycle, another series of reaction that takes the byproduct of glycolysis. So what you're left with after glycolysis is done goes into the Krebs cycle as pyruvate, or it's converted to acetyl coenzyme A inside the mitochondria. that metabolite from glycolysis called pyruvate goes into the mitochondria and goes through another series of reactions that breaks it down and charges up FADH2, it charges up NADH, and it charges up ATP. So the Krebs cycle actually really, the Krebs cycle inside the mitochondria gets us way more ATP in the end. Glycolysis. Glycolysis is just the initial stage of chopping up glucose. In the cytoplasm. And then finally, we have the electron transport chain. So the electron transport chain you can think about in terms of like a currency exchange. So we have a bunch of NADHs, we have a bunch of FADH2s, right? And what we do is we drop their electrons off onto this like we drop their electrons off onto this transmembrane system that takes those electrons and converts their energy. It converts them into ATP eventually through the help of ATP synthase. And we'll talk about that in detail. But all of these processes are all facilitated by enzymes, right? And we'll talk about them in our next videos. So thank you. That's the end of that one. And I'll see you guys on the next one.